హలో. సురేంద్ర కుమార్ గారు, డాక్టర్ పి సురేంద్ర కుమార్ గారు, కెన్ యూ ప్లీజ్ టాక్ టు మీ? డాక్టర్ పి సురేంద్ర కుమార్ గారు.
Sir, yes, sir.
Good morning, sir. You are from which college, sir?
Bapat Engineering College, sir.
Bapatla Engineering College. Okay, sir.
Sir, what?
Hello.
Sir. Yes, sir.
Sir, can you please share the feedback on during the last session, that is on Saturday? Probably between 3 to 4, evening 3 to 4.
Yesterday, sir.
No. Regarding the feedback on entire entire induction program, 1 week induction program, because during the valedictory we will be asking some of the faculty members to share their feedback, overall feedback.
Okay.
So can you please share your feedback on during the valedictory session?
Sure, sir. Sure.
So be ready with your genuine feedback on the last session between 3 to 4 on Saturday.
Okay, sir.
Yes,
Sure.
Sir. Amarnath Sharma, sir. Hello. Amarnath Sharma.
Hello, sir. Hello, sir. Good morning, sir.
Good morning, Amarnath Sharma garu. Can you
Yes, sir.
please
Very good morning, sir.
Can you please share your feedback on this induction program during the valedictory session?
Sure, sir. I will share, sir.
It is between 3 to 4 on Saturday, that is 21st of this month.
Sure, sir. I will share, sir. No problem, sir.
Okay, thank you, sir.
Thank you, sir.
Sudharani madam. Hello. Sudharani madam, can you please unmute your mic? Swati Lakshmi madam from PVP SIT. Hello, Swati Lakshmi madam, can you please unmute your mic? Sudharani madam, Sudharani madam. And of course, every participants can share their feedback. There is no issue, but at least we could able to identify few people, so that if we call to share your feedback, at least some of the participants, they must react to that. That's why we are trying to identify some of the people who are continuously participating. So anybody can share their feedback. There is no issue in that. Josna madam, can you please unmute your mic once? Hello, Josna madam. Joshna Bhagirthi, can you please unmute your mic?
సార్ అంటే టైం ఇంకా ఉందని ఏమన్నా పక్కకి వెళ్ళారన్న సార్ ఒక సిస్టమ్ దగ్గర ఏమన్నా లేరేమన్నా.
హలో ఋషి సార్.
సార్
చెప్పండి.
అంటే పార్టిసిపెంట్స్ మామూలుగా
Ah.
జస్ట్ ఆన్ చేసి ఉంటారు సార్. అంటే 10 మినిట్స్
Okay.
కొంచెం టైం ఉందని
అదే
వాళ్ళ
అదేలేండి.
సిస్టమ్ ఉంది ఏమన్నా లేరేమన్నా అనుకుంటున్నాను.
అదే మళ్ళీ తర్వాత ఒకసారి సెషన్ లాస్ట్లో మళ్ళీ ఒకసారి అనౌన్స్ చేస్తాను.
ఓకే.
Rishi sir. Hello, Rishi sir.
సార్
As the same person is delivering the lecture in this morning, we need not read out the biodata.
ఓకే సార్.
So after formal welcome, we will ask him to start his session.
ఓకే సార్.
Okay. So for the session, there is no readout of the biography of the speaker.
ఓకే సార్. ఓకే సార్.
Okay. Thank you. Hello, Mr. Ramesh Deshpande. Can you please unmute your mic? Ramesh Deshpande.
Sir, good morning, sir.
Sir, good morning. You are from which college, sir?
BVR Reddy, sir.
BVRIT Hyderabad.
Narsapur.
Narsapur. Okay. Sir, could you please share your feedback during the valedictory session of the induction program? That is on Saturday.
On that day, I have class, sir.
Saturday evening 3 to 4.
Yeah, that's why I'm telling. But other day we have meeting.
Okay, so
So
you
if
are
I
not.
possible, I will. If I join, then I will give the feedback. Otherwise,
Okay. We will ask during the session. If possible, you can give the feedback. No issue.
yeah. Okay.
But on the Saturday between 2 to 3, you have to write the test.
Oh, only on Saturday only.
Yes. Already it is
Only
given in the
particular
session.
time only, or else you have any
Between 2 to
one day
3.
time like that?
Between
Only
2
2 to
to
3
3.
only.
Yeah.
Oh. Okay.
It is already given in the session at the very first of the induction program itself. You just please, you can plan accordingly.
Okay, sir. I will plan. Thank you, sir.
Thank you. Sir, somebody is joining the program with the name Ellen's iPhone. Ellen's iPhone. Rajshekhar sir, speaker has joined just now.
Good morning, Dr. Ramakrishna.
Very good morning, sir.
Right. I think
We will start the session in a few minutes.
Yeah, just is only
Okay.
I
Yes, sir.
started because to avoid
Yes,
any
sir. Yes, sir.
disturbances.
Yes, sir. Rajshekhar sir, can you please make yes, you are connected to co-host, sir. Yes, it is ready. Okay, participants, welcome to the fourth day of the induction program. Today, today morning we have the second session by Dr. M. Lakshminarayana garu. Today he will be delivering on millimetric wave phased array antennas. In the afternoon, we have another session by S.D. Gupta from IIT Bombay. We hope you will enjoy these two sessions and you will get maximum benefit out of these sessions. Thank you all. Dr. Lakshminarayan sir, you can start your session, sir.
Okay, thank you, Dr. Ramakrishna garu.
Welcome, sir.
I think I should go on screen share mode. Are you able to see my screen?
Yes, sir, but not PPT, sir.
Okay, I think it has come out, launch meeting. It came something like launch meeting. I don't know, it should not have come. Dialog shown browser. If you don't see the dialog, click launch meeting.
No, sir. Actually, you are in the meeting, but I think it is another window.
Okay, right?
Yes, sir.
Now,
Yes, sir.
is it visible? My screen
Yes,
is
sir,
my
it is
screen visible?
You can select the. You can select the window now.
Right.
Yes,
Okay.
the PPT is visible.
Right.
Application of millimeter frequencies, but I think it is yesterday's PPT.
Oh, right. Okay. I will go to the other one. How to open? Okay. Is it not? Is it right? Millimeter wave phased array
yes, sir,
antennas.
millimeter wave phased array antennas.
Right.
It's right, sir.
Okay. Right.
Yes, sir.
I think
Now it is ready for presentation.
Ready. I think it's ready. I
Ready,
think
sir,
I'm Dr. Ramakrishna garu. I may have to log out at dot 12 o'clock if situation, because we have a meeting with Air Force Southern Command, right?
Sure, sir. Sure.
If that gets delayed, I will continue. If any question answers, if it remains, I will come some other time, either tomorrow or today afternoon, and clear the doubts. But for the purpose, just I am informing you, most likely it may take to 12:30, but I do not know. Normally, it all depends upon the services. Okay. Good morning to everybody, all the participants. Hope. I think the number of participants is going down. Yesterday also I found a bit less number of participants, because this is normally not very exciting topics, particularly related to antennas and other things.
A small submission, sir.
Tell me.
Actually, the number of participants are around 20-30 at the starting time, but later on, within a few minutes or within half an hour, it is raising to 50 to 60.
Okay, good.
But actually, we want to start the sessions exactly at the scheduled time. That's why
this is good practice, Dr. Ramakrishna. I fully appreciate it. Right?
Thank you, sir.
Let us go ahead. No problem. It will work out. Okay.
Okay, sir. Thank you, sir.
Yeah, good morning to all the participants, and I thank Dr. Ramakrishna and Gudlavalleru Engineering College for giving me this opportunity to speak on millimeter wave phased array antennas. See, before speaking, just I would like to have a little bit of this thing. Way back in 1980s, when I joined DRDO, that time itself we were talking about, but that is early 1970s only it started the phased array antennas. I had an opportunity to work for the development of 16 element linear phased array antenna for identification of friend or foe applications. That has gone into the system, which is the Rajendra radar, for launching and tracking of, Akash missiles. With that one, actually, that was one of the most complex design those days for that technology. Now, as we go along, I had again opportunity to work in cylindrical phased array antenna. Then after that, number of other antennas. And during my PhD in United Kingdom, I was exposed to 94 gigahertz, but was a very brief time. That is in 1990s, 1990. I mean 2088 to 1990, right? Now, I have a passion to work in antennas. The number of slides looks to be more here, but it does not matter because to keep the talk as a unity, I kept some of these things. I will skip some of the dummy or which were already discussed, for the purpose of to keep the topic intact or integrated, right? Though Dr. Anjaneyulu spoke something on antenna applications, right? He has put certain things and I am supplementing some more things here. Since some people will be there without earlier background of antennas, only whatever that, third year, second semester, or whatever it is we have, academic, only that will be there. And those of some of the participants may have already heard my presentation earlier. For them, it may be little bit of repetition, but after that, then we take over millimeter wave frequencies. Whether it is a millimeter wave or microwave or VHF or any of these things, the principles are same, but technology keeps changing. So starting with the definition of IEEE definition, antenna is that part of a transmitting or receiving system that is designed to radiate or receive electromagnetic waves. See, you may be seeing the first definition also. First definition goes purely a antenna is a transducer, but it is a system. So this covers a broad definition for antenna, means it can be a phased array antenna also, transmitting system, or it can be a receiving system. So this is where the IEEE definition is very broad and good. Now, see, this serves two purposes. Those who are attending, particularly the participants, every participant need not be an antenna designer. But I am sure 100% of the participants, including the faculty, all are using the antennas in one way or the other. The bigger example is, broad example is the mobile phone. The mobile phone is having antennas, right? If you see that, the moment an antenna is required, we need to specify its frequency of operation and its coverage. Means, suppose if I sit in a room, will it cover the, will I get the signal? Suppose if I stand in an enclosure, particularly lifts, when we go, sometimes metallic lifts will be there, we don't receive the antennas. And other properties, gain, input impedance, bandwidth, polarization. So these properties are required. We need to know what it means. I will not be going through the details of these things, but these parameters are required for any system engineer. Suppose if you are designing a mobile phone, let me say, when you design a mobile phone, can you say that I want to use reflector antenna? Definitely you cannot. And you don't even utter that word. If you utter that word, somebody will laugh. So definitely I should choose a printed antenna. Then comes to the size, comes to the gain. So these are the things which we need to know, particularly for the utilization purposes. I take only two things. One is the radiation pattern, which is very important. Another is the gain. See, radiation pattern is a graphical representation. You see, suppose if a signal is fed here, let us take a dipole here. Its signal in the throat, it is a three-dimensional pattern, right? Now, but three-dimensional pattern we cannot view. So we tend to take that, two-dimensional principal plane patterns. One is the field pattern, another is the power pattern. In anechoic chambers, for antenna performance, whenever you ask or whenever a supplier gives, we get the power pattern, right? We get the power pattern. Now, if you see that power pattern, there is half power beamwidth, means power is half. Suppose if we take a normal scale, if it is a 1, we have to take the beamwidth at the half power beamwidth. Otherwise, if you go to the dB scale, it is between a 3 dB. 3 dB is nothing but this thing. So not only this, for a directional antenna, which is going to have side lobes, right? This is nothing but is equivalent to any communication system. We work sin x by x function, sync function, or whatever you call, right? Now, if this level of side lobe is very higher, means suppose in this case, deliberately we are showing only 9 dB down. If anything coming in this direction, this lobe also will receive, this lobe also will receive. In such conditions, when this antenna is moving, this also receives, means a side lobe detection, which is not a good requirement, right? This is where radar does not need this. Okay. Importance of side lobes is this, means wherever depending on the applications, we should reduce the number of, the side lobe level. For instance, a radar antenna with ultra low side lobe means side lobe level as low as 35 to 40 dB down compared to the main beam. That is another big challenge in the antenna design. Whether you design, the moment if I say antenna, it can be a single antenna or it can be array antenna, right? It can be a microwave antenna, it can be a millimeter wave antenna. So most of the antenna work we discuss here is frequency independent principles. These are all frequency independent principles, right? Over the last 60 years, if you see this, the number of antennas are all, dipoles, monopoles, loop antennas, slots, microstrip. These names are known to all of you, and mostly any other antenna which comes will be a subset of this family of the antennas, right? Just for the purpose of, these things, an antenna called an aperture antenna is like this, right? A horn antenna, right? A reflector antenna is an aperture type of antenna, and a normal wire dipole, these are called the wire type of antennas. A slot array is also an aperture type of antenna, right? If you go through, suppose if this, the famous chip, microstrip antenna, this is an also aperture antenna, right? Microstrip antenna, right? This is the most very popular antenna. This we have discussed at length. And other antennas are reflector antennas. Before these arrays came, mostly people were using the large reflector antennas for getting the higher gains, right? Now, another parameter is the directivity and gain, whatever you call, both are interrelated. This why I am discussing is, see, in the where my team of youngsters, see their team, my team of youngsters are hardly, they are all about less than, average age is about 28 to 30 years, less than 30 years average age, mostly 27 years. They will rush to me, sir, I want an antenna. For what application? Drone application, right? What do you want? Sir, I want a 13 dB gain at 2.4 gigahertz or 5.8 gigahertz, 12 dB gain. Okay, 12 dB gain I will suggest an antenna which is available. But sir, I want 60 degrees, say 70 degrees in elevation beam width and 20 degrees in azimuth beam width. How does it happen? It cannot happen. Or there is a limitation. That means gain and the beam width are interrelated. So I am not reading the definition. Definition is everybody knows. Here, if you see this, the total power radiated is nothing but for a taken radius, it is the total surface area of this which you are taking out. 0 to means it's a sphere. Surface area of the sphere we are taking. It is spreading like that, right? So for the purpose of understanding, we take omnidirectional antenna or isotropic antenna, not omnidirectional. Isotropic antenna is like, it looks like a sphere ball. So this isotropic antenna means if I give 1 watt of power and radiate in all 360 degrees, solid angle, 2 pi solid angle, right, this will give like a sphere, this thing, right? Then if you take this, no, I want I don't want in full all directions, I want in a only particular direction, means this is called gain in this particular direction. So particularly my suggestion to this thing is particular, of course teachers definitely understand and know this, they are anyway teaching to them, but once we write the examination, people will forget about that. Students will forget about that. The gain is not a gain like an amplifier. Gain is in a particular direction, right? That is here power delivered to the antenna and power radiated by the antenna, right? Power given to the input of the antenna, power radiated by the antenna. Suppose if you consider a parabolic reflector antenna for high gain antenna, whatever you take it like that, so the beam width is only 58.4 lambda by degrees, right? Where A is the area of the aperture, D is the diameter of the parabolic reflector, wavelength is lambda, eta is aperture efficiency. If you keep everything constant, right? Keep everything constant, what will happen if you want to use, if you want a gain of 30 dB, right? If you want a gain of 30 dB at 6 gigahertz, I need an aperture size of 62.4 centimeters. For the same gain, if I reduce the frequency by half, I need to increase the diameter by 2 times for the same beam width. Look at that. For the same beam width and same gain, if we double the frequency, we will reduce the size by half. If we halve the frequency, double the size of the aperture. It need not be reflector alone, it can be an array also, right? Just 1 second. Sorry, I have to switch off my fan, right? So this is the principle. That means aperture size, gain, and beam width. These are interrelated, right? Now, we go to the arrays. Even the array is developed, the concept is developed from the, sampling of the continuous aperture. The array theory is also developed from the continuous aperture. So the types of arrays are linear, circular, planar array, and conformal array. These are all discussed a little bit. And when we design, what are all the things we need to take? There are several array design variables. First of all, just now we mentioned that, okay, frequency, I take 28 gigahertz, 60 gigahertz, or 90 gigahertz, whatever it is, right? I take this and, the frequency. Once I get the frequency, yes, I want some gain, 30 dB, 40 dB, 60 dB, whatever the gain is required for the millimeter wave. But for the other things, it is for the same aperture, it is the lesser. See, listen, this particular one I just told, I will repeat again elsewhere, which is very much required, right? Now, when we use the independent elements, what should be the difference between the elements? What should be the difference between the elements? I mean, the distance between the elements. If it is a planar array, if it is a linear array, what will be? Then one important thing is any antenna, we normally call antenna, but antenna has got two parts, at least minimum two parts. One is the feed, another is the radiator. If you take the, even microstrip element, if you take one microstrip patch antenna, we say the type of patch mean microstrip feed or probe feed or slot, electromagnetic coupling feed. So type of excitation, and since the number of elements are involved, am I exciting all the elements with uniform amplitude? Means excitation amplitude and excitation phase of the elements is very important. Well, this itself is the whole array part of it. Take the array, decide the frequency, choose the configuration. Suppose if I want a, let me say, symmetric beam, I will go for a square array. If I want a azimuth very narrow, elevation very broad, I will take a linear array. Like that, we have to choose. It is not that they beam within two principal planes, we have to decide before going to that. Now, let us straight get into the linear array principles. Right? First of all, if you see here, linear array is composed of a number of elements. Each element is fed by a phase shifter, because we are talking about the phased arrays. If you do not keep any phase shift, let me say all elements are equal, fed with equal amplitude and equal phase, this will have a single main beam at the bore side that is perpendicular to the plane of the array, if you take a planar patch array or whatever it is, right? But why should I do that? If I take such an array, but if I want to throw the beam to see different direction, then what will I have to do? I have to move the antenna physically. Got it? Suppose if I take an antenna, just let me. If you see, hope you are able to see. If this is my antenna, let me say, if I put all equal phase and amplitude excitation, it will have a broadside beam. But if I want to move to elsewhere, I have to rotate this physically. So that rotation we need a servo, and that is not a that can be avoided with the present technology. Using each antenna can be connected with a phase shifter, right? So number of phase shifters are there. So see, you can see this is the phase front, right? Equi phase front for each one. The profile, the trajectory of this thing is the tangent connected with all these equiphase fronts will become a array wavefront, array plane wavefront, and the direction of radiation will be orthogonal to the phase front, wavefront or phase front, whatever you call. In this particular one, this we will have, see, delta phi means the phase, it will be 2 pi d by lambda sine theta. Theta is the direction of radiation, right? If direction of radiation is equal to 0, let me say delta phi is equal to 0. Sine theta is equal to 0 means delta phi equal to 0 means all elements, there is no phase progression. All elements are fed equally. Otherwise, what will happen if the beam angle is a function of the phase shift? Then this we have to use this particular one. We need a particular combination, right, to avoid grating lobes. Grating lobe means what? Suppose if this is actually three beams are coming, right? We need only actually one beam. This is suppose n is equal to 8 element array. D by lambda means I am using 1.5 wavelength deliberately to explain to you. It shows these are the 3 beams. These out of 3 beams, these 2 beams are not real beams, but still they get lot of there will be a wastage of energy and coverage is lost for us. We will be getting only from 0 to somewhere like 20, 30 degrees only, right? Suppose if I take d by lambda is equal to 0.5 or half wavelength, I will be able to cover with whole area with a single beam and little bit number of side lobes. So for this reason, so this is the to avoid the grating lobes. Suppose why this should be greater than 1? If this is not greater than 1, sine whatever the value, sine inverse more than 1 does not exist, right? The argument has to be between plus minus 1 only for this one, right? Now, getting into little bit slightly properties of the linear arrays. Suppose if I use only one element, it is an isotropic. I use 3 elements, it is forming a beam, main beam, right? If I use more number of elements, what is happening is, you see, the beam width is getting narrowed, number of side lobes are appearing, right? If I use, instead of I use again phase shifters in between for each element, I will be able to scan the beam in the direction which I want. So the primary reason for using the arrays is to produce a directional beam that can be repositioned at any area, at any place we want, right? Now, okay, this is a normal mathematical part of it. I will just tell the, this one, simple one. This is the one very simple one. Same ultimate equation is here. In any array, linear array or planar array, in any array, the total array pattern is the product of array factor and element factor. Now, what is this? Array factor, suppose let us say that let us say that some 10 by 10 array is there or 16 by 16 array is there. The array factor is the radiation pattern of the array, consisting of replacing them as from the all are isotropic elements. If all elements are isotropic elements, that particular array is called that pattern is called array pattern. But normally, in the practical situation, we never use isotropic pattern. So we use that element factor, a practical element factor. The moment we multiply with the factor in element factor, that becomes the real full antenna radiation pattern, right? For an antenna radiation pattern, for a linear array or for a linear array, this is equal to 1 over m sine m psi by 2 by psi by 2. M is the number of elements, right? D is the inter-element spacing, beta is the constant phase delay, right? Now, constant phase delay means from one element to the other element. Just now I showed to you, right? Now, if you see here, for some this appears very good. Sine psi by 2, sine psi is equal to kd cos theta plus beta. Normally we leave it there and we leave it just like that. Suppose if I kept it deliberately here, this is a very general equation where it can be any direction, this particular array, isotropic sources. But the moment if I say that my array is in the z direction, this is the equation I should use for psi, kd cos theta plus beta. That means a vertical linear array. Suppose if I have a horizontal linear array, then there will be a sine theta cos phi. Instead of cos beta will be replaced by sine theta cos phi with the x-axis if the array is along the x-axis. If the array is along the y-axis, kd sine theta sine phi plus beta. So this is the condition. That means whenever we work for the linear arrays or any array antenna, we need to be very clear that the coordinate axes have to be specified, right? Okay. Now, looking into this is one of the linear arrays under measurement. So it looks like this. Just I am showing a to feel of that how a linear array, it can be a circular patches or it can be rectangular patches also. Now this I have already explained. Major number of lobes, right? And changing beta will steer that beam peak and condition for no grating lobes. This all I have already explained here, right? While explaining this, right? The same thing I put it in the word format. Now, let us say that this is a little bit more interesting. And mind you, this is applicable irrespective of the frequency of operation, right? As long as whenever we work with wavelength, this is valid for microwave as well as millimeter wave, all the wavelengths, these principles are valid. Suppose now, I told in the beginning two important things. One is the radiation pattern, another is the gain of the antenna, right? Gain of the antenna, we have already told that it is dependent on the physical aperture area, effective aperture or aperture area. Now, if it is a reflector antenna of 1 meter diameter, means 1 meter. There is nothing like that. But if it is a linear array or planar array, if I say that linear array, let me say 10 elements, means I can have the flexibility of the inter-element spacing. Shall I increase, shall I decrease, or shall I keep each element at 0.25 lambda or 0.5 lambda or something like that? What will I do? That is one way. And another is, if I want to increase the number of elements, if I want to increase the array size, I want more gain, array size. If I increase, shall I add more number of elements? Yeah. If I add 5 elements, we can get, this is the pattern. Okay, I will take the half wavelength itself and increase to 20 number of elements is 20. So the array size has become, right, 10 wavelengths. When the array size is doubled, the gain is increased by 3 dB, right? 3 dB increase means double the gain, right? Then array size is again increased by doubled, then another 3 dB is increased. That means as we increase the array size, suppose if we take half wavelength inter-element spacing, gain is approximately proportional to n or almost equal to n, because d by lambda is equal to half, right? This is equal to 2, gets cancelled, and for a broadside array, number of gain is equal to number of elements. You see, you take log 20, log 40, you will get only these things only, gain, right? 10 log if you take it. So that means the summary is, the number of elements is increased with keeping the array spacing same, means we are increasing the aperture size and we are increasing the gain. That gain increases almost, as the array size is doubled, gain will be increased by 3 dB. And the beam width is half, it will get directly half. Suppose if it is here 20 degrees, right? This will become 10 degrees, this will become 5 degrees. This is the theory behind this. In the similar way, we have, increasing array size by inter-element spacing. But by the moment if you start increasing inter-element spacing, the grating lobes will come. Suppose if we have 0.25 lambda, array size is, say 0.25 lambda is the separation, and array size is 2.5 lambda, then same number of elements is same. I have got same number of elements, but I keep on changing. Any separation until half wavelength, the gain increases and this becomes optimum. Of course, little bit also the gain increases, but the moment as we still increase the separation to 1 wavelength, see, grating lobe will come. That means I am able to utilize this antenna up to plus minus 90 degrees with lambda by 2 spacing or lambda by 4 spacing. The moment it is lambda spacing, I cannot use the antenna more than about 50 degrees, plus minus 50 degrees. This gets restricted. Okay. Now, well, in the beginning I told antenna elements need not be excited with all uniform. If we excite with all uniform amplitude, the first side lobe will be around 12 to 13 dB only, right? For the circular aperture, it will be about 17 dB. But if we push down to the side lobes are pushed down, means different elements have to be, there should be a taper we have to follow. That taper means central element I will give full 1 unit, second element 0.9, third element 0.75, fourth element 0.6, something like that. If we taper that excitation, then the side lobes will go down. One of this thing is the Taylor pattern, 40 dB Taylor pattern. The side lobes are pushed to 40 dB down. What is the effect then? When the side lobes are pushed down, the beam width will get broadened. So this is the another effect, right? Now let us quickly come to the planar array. Now uniform planar array, you see planar array is nothing but array of linear arrays, right? A uniform planar array is nothing but array of linear arrays. This gets, again, see, if you are having with in the x direction sine m psi x by 2, this will become one more will be added. So pattern of one linear array to other linear array, this is the product. So this is the very easy mathematical approach. Here again, the restrictions are to scan over the space without grating lobes. We need to have spacing along the x-axis, x direction is again less than lambda by 2, along the y also less than lambda by 2. This is the planar, and the direction of propagation will be along the z direction, right? Now, in order to analyze or in order to understand the grating lobes, excuse me, we use analysis by sine UV space. That means, see, if I see in the spherical coordinates, right, for studying the grating lobes, this is a unit circle. This does not look like, because this is three-dimensional pattern. This unit circle, if I map it onto UV plane, UV means U is sine theta cos phi, V is equal to sine theta sine phi. These are nothing but the directional cosines. Then this will give a unit circle. This representation is always very comfortable for the analysis. Projection of XY system on XY plane, projection of the coordinate system on only XY plane. We are not considering the, right, Z. View from means we are looking from the Z axis, but only this thing. So if you do these things, what will happen is, grating lobes, we will not discuss of grating lobes of planar, linear, because most of the time we use planar arrays, particularly in the millimeter wave region. Now, one method is I will have the elements like this, right? Like a grid combination. Another is a triangular grid combination, means slightly different next row like this. So here, any three elements, if you connect it, it makes a triangle. Whether it is a triangular or square grid, the restriction is the spacing along the y-axis should be lambda by 2, and the x-axis and y-axis should be lambda by 2 only. dx dy is equal to lambda by 2. Then for this scenario, if this type of spacing is there, you can see that the lobes are at 2p. See, suppose this x and u and v, this is at element number at 2. Grating lobe will be at 2. So that means in this is the unit circle represents a visible area, right? In the visible area, there are no grating lobes. So then if we use a triangular grid, we can have number of elements, 14% number of elements are less, and there are no grating lobes for scan angles less than plus minus 60 degrees. We can go up to plus minus 60, but most of the time, many applications take plus minus 45 degrees, right? So for rectangular grid, half wavelength spacing, there are no grating lobes will be there. Now, if you see, why should I keep lambda at lambda? Suppose if I increase the inter-element spacing to one wavelength, right? When I increase the one wavelength, you see, when it is half wavelength, red dots are away from center dots by 2 times. If I take to the 1 lambda, then all dots are coming at 1, 2, 3, 4 grating lobes are appearing for the one wavelength spacing, right? So this is the importance of this thing we need to avoid. This is the one of the important observation, right? Now, what will happen is, if now these two are the static arrays, I am not scanning the array. Suppose if I want to scan the array, what will happen is, grating lobe, suppose if this is there, this is theta is 0, phi is equal to 0, theta is equal to 0. I am not scanning the array. This is at the broad side. But still the element spacing is half wavelength only. The moment if I scan this to 90 degrees, right? Theta equal 90 degrees, automatically this will be moving to the visible region. So this is where scanning affects the grating lobes. Lobes will be shifting to the visible region, right? Now, if you see this, all these things, this is anyway I have shown here. This I already shown here. The right side one you see here. The top one is 8-element array, half wavelength space, right? The bottom one is the bottom of the bottom one. This is the 64-element array with 32 lambda line source, right? Suppose instead of keeping this my half wavelength, if I keep wavelength at 4 lambda, same. See, I want to implement an antenna of 32 wavelength size antenna. For 32 wavelength size of antenna, the best method is I should take 64 elements. 64 elements if I take, this is the very good pattern. Please see carefully. No. Why do I want so many antennas? Still 32 wavelengths, I will cover only with 8 antennas. Yes, you can cover. Who told? But this is the consequence. You will get the main beam as well as 4 other grating lobes. So that's the reason the antenna element spacing is very important, right? Now, another this thing is we told that generate a single beam and scan it so far without the grating lobes. Now, why do all this problem is there? Another method is have a multiple beams. Keep the antenna spacing same, have 4 elements or 10 elements or 20 elements, have the multiple beam antennas. So multiple beam antennas can be have it using a method called the Butler matrix, right? Suppose let us not get into very big terms. All of you definitely know a hybrid. Hybrid is a 4-port device having 2 inputs and 2 outputs. If I excite at one input, let's say 1 R, the phase at the output is equal and 90 degrees out of phase. Suppose if I put here 1 watt, this will give output half watt with 90 degrees. Then if I connect 2 identical antennas here, what will happen? If you take this one, if you calculate this one, the beam will be tilted to 90 degrees from the vertical both sides. The same thing, if I connect the input here at 1L, right? Here the phase again 0 to 90, this will be shifted by another by 30 degrees. That means if I connect 2 elements and if I switch between the inputs, if once I excite this, means I have a SP2T switch. If I switch here, so that I can cover some area with 2 beams. So this principle is very important for having multiple beams, particularly for the cellular communication. This can be utilized. We know that we need discrete, suppose in a particular direction the traffic is more, I will put only beam in the direction, right? If we go to the little bit more, there is a 4x4 Butler matrix, means here we need 4 inputs and 4 outputs. Any Butler matrix will have n inputs and n outputs normally. So here I can have 4 beams, 4 inputs, 4 beams I can have. Here, one typical difficulty with the hardware components is, suppose if I say that this is element number 1, element number 2, element number 3, element number 4. These 4 elements, I have to connect, second port of the hybrid to the third element, and first port of the fourth hybrid I have to connect to second element. That means there is going to be this thing, you know. So this is fine if it is cables are there. I am taking, suppose there is an SMA connector, I will connect this by one cable, equal length cables, fine. But in the printed condition, how do we do this, right? This is where, of course, phases, this can create, this can have, you know, for port 1, this is the phase progression, port 2, this, where the phases are coming, we are utilizing the, you know, fixed phase shifter. Suppose if I take here 0, 0, this also 0, 0, then here it is taking 90 degrees, right? 90 plus 40, 135 degrees, right? Here again 0, see, like this goes to 135 degrees, like that, right? This goes again, so that phase progression will be there, 0, 45, 90, 135, actually for one beam. If you take the port 1, port 2, port 3, port 4, this will generate 4 beams, 41.4, 75.6, 104.5, 138.6. This is the, you know, beam patterns. Now what does the, when you know, theoretically when I show everything is fine, you know, all are at equal, there is no loss. But if you get into the practical ones, it is a little bit down, because this is due to the element pattern, this is due to the isotropic elements, right? Now this is again you know, a practical array utilized for cellular communications. Similarly, that it goes on, all that it requires is hybrids and fixed phase shifters. These fixed phase shifters will have certain rules which will explain little bit, right? The number of beams is equal to the total number of elements. The number of beams formed is equal to the number of elements used. Now suppose, let us say, immediate part 1, this is, you know, 8 by 8 Butler matrix, we got, see, 8 beams we are getting. But how many hybrids we are having here? If you see, 12 hybrids, right? Oh, sorry. Right. Number of hybrids, n by 2 log n, log base 2n. If n is equal to 8, this is equal to 3, n by 2, 8 by 2, 4, 4 into 3, 12. We need to have 12 hybrids. Number of phase shifters is equal to log n to the n minus 1. This 3 minus 1 means this is equal to 4 into 2, 8 phase shifters only we want, right? See, 8 phase shifters, 4 here and 4 here, like that. See, but how to do these things in a particular way? You know, we need to have sort of, just now I told earlier, you know, how to control the port, this thing. See, this is a hybrid junction properties. If I go to, for interconnecting crisscross, you know, these things, we need to connect, design like this, a crossover, we call it as a crossover, right? In a planar construction, a single layer implementation of Butler matrix crossover must assure, it is, suppose if I put, suppose if I excited port 1 in the normal you know, what will happen if I put a port 1 equal half, suppose if I put a 1 watt power here, half watt by 90 degrees difference. But if by between this one, if I say port 1, if I excite here, the power is going to only to the port 3, right? Port 2 and port 4 are isolated. It is only just, you know, one is minus 45 degrees. In the same way, if any input comes, this is, suppose if I connect an antenna, if I connect to one signal here, connect to the antenna here, even if I connect another antenna here, it will not reach this particular signal. So similarly, if I connect, if while receiving, if I receive a port 4, if I connect the input at port 4, it will appear at port, you know, 4 at 2, port 2, S42. This is the, so that means crossover design is very important for here, you know. This is where we have to design. This is one of the, my MTech students has designed this particular one. These crossovers are important for having a Butler matrix. straight. Otherwise, we could have from this connector here, this we have to connect here. That is not possible, right? See, this is port 1, then this will become port 2 now. Otherwise, this would have become port 2 earlier, right? It appears like this, right? Now, utilizing this particular concept, scanning an array, suppose if I will have some 32 elements. Now, if I will have a circular array. In the circular array, what will happen, right? The elements, in the circular array, suppose if we excite with variable phase shifter, let me say. When you excite a variable phase shifter, it is very easy to visualize for a linear array. Okay, I'm getting here, and then what will happen to a circular array? Circular array will generate modes. If all are equal phases and this thing, it will generate an omnidirectional pattern with gain. Otherwise, depending upon the equal phase shift, phase progression, we will have a particular directional beam and we can steer that beam. Single directional beam can be scanned. Of course, I don't dwell this more because this is not a very popular. I just leave it for the principle. Why I am explaining these things is, suppose while doing certain things, the things which are abandoned earlier in 1940s and 50s can be revisited with the new technology. That is the idea of talking all these things, because millimeter wave antennas are just coming up. Means they are coming up means, can we adopt the existing technology? That is where the importance is there. That is the reason we have to review our existing technology also. Suppose if what will happen is, when let us say that n is even for this Butler matrix, 32 is there, and if the kth port is energized, means kth port means here this is the port number of ports, this is a Butler matrix, right? If kth port is energized here, right, what will happen is the difference in phase between the adjacent ports is 2 pi k by n. Suppose if it is a first port, it is a 32 elements, it is the phase shift is each will have 22.5 or 11.25, right? Like that, it will be there. 2 pi k is equal to 1, n is equal to 32. 32 by 2 by 32 is equal to 1 by 16, 11.2, something like that, or whatever this, right? So this is one Butler matrix number. This digital bearing discriminator, the word is digital is used here. The bearing can be decided with digital steering, right? Yesterday I was telling, I think some while talking about the substrate integrated waveguides, between the holes there is number of, we are what is that called, implementing the waveguide into the dielectric, where I mentioned that what is the difference between the holes. This is similar to a grid reflector antenna. You see, if you can see here, grid reflector antenna, this is only forward direction only. If any antenna receives the waves, it will not leak outside, right? See, this is where this concept is important. This is frequency dependent, and the array is here, right? The digital bearing discriminator array is here, and these are the antennas, certain antennas we are keeping. Of course, this is one of the system where I was the program director for this, right? And another this thing is also lens are another important antennas. One most important antenna is the Rotman lens antenna, right? This Rotman lens antenna, this uses time delay for beam scanning. What does it mean, right? If I throw, see, let us say take this as a I will take directly to, this is the Rotman lens. In the Rotman lens, we have got beam ports, right? These are the beam ports. These are called the array ports. Here, it does not look like a lens the way we expect. The moment we expect lens means, is it some convex lens or concave lens? Yes, still if you take the cut, it's again, is a concave type of contour, right? Right. If a beam, one port is excited, this will have a different path lengths, you see, across the 15 ports, right? Beam number 1 to beam number 15. So any signal which is, excited here will reach at different time points. Means this comes a bit immediate early, right? And this comes a bit late by the one, see. So this is where the one which comes early will go forward, right? The ones came late, see, this is the wave front for the port number 1. Similarly, for the port number 15, what will happen? This will be the last one and this will be the first one. That means beams will be formed like this. Here, this beam direction is independent of frequency. We are not talking any frequency point here, right? Each beam possesses the full gain of the array aperture, and this has got the small size, lightweight. This has been implemented up to 18 gigahertz. I think 26 gigahertz also we have this type of lens antennas, right? Now this is the mathematics. Let us not worry about this. Is standard is available here. The importance is the focal angle and maximum scan angle. This beta maximum scan angle, we need to look at it, right? So this, well, if you see here, what will happen here is we connect some more circuitry here, right? Just 1 second. I think I should switch on my, right. Sorry. Because I forgot to switch on the power for my laptop, right? Okay. If I put here, or I can choose any of the beam, each port will give me a beam, right? This beam processing here, this is, of course, this is a laboratory model. It won't be that crude in the, this thing. And this is a linear array. You see, this all appears to be like a one rectangular waveguide, but it is not so. Each one has got certain thickness here because it has to withstand some power, right? This is required for high power application, means jamming applications. This will be mounted on a ship or something like that to protect the ship like this. The moment if any attack comes, we need to throw number of beams here, right? Number of beams here, right? See, this is the beams here. If you see again here, the last beam, as we go from the bore side, the amplitude reduces. This is equal to the, the gain follows the element pattern profile, right? Right? Sorry. Now, another this thing is, I have shown to you with the Butler matrix. I have shown to you with lens, and another is I switch the beam electronically, switched beam array, right? I'll just take a part. This also I am the designer for. I designed this in 1996 for one of the systems, where if you see that this particular one will be on the high-sted self-supporting mast of about 50 feet. This will communicate to the other systems which are about 20 to 25 kilometers away, any system. Now, in that way, why do the 25 kilometers are there? Why can't I have the omnidirectional antenna? No, because problem with omnidirectional antenna is if I radiate here, everybody will receive, but I don't want everybody to receive. I want only to transmit to those particular individuals, systems with whom I want to contact. This is what is called the protection or electronic protection, ECCM, electronic countermeasure properties. This will produce here at any given time we will excite only 4 elements at a time. 4 elements in the sense 4 columns. Each column is having 4 elements. So if I will excite for the beam number 1, I will excite 1, 2, 3, 4 columns. For beam number 2, I will say 2, 3, 4, 5. Beam number 3, 3, 4, 5, 6. Like that it goes, right? It will produce 16 beams because it has got 16 arrays. SP40, and these are called the transfer switches. Transfer switches will take care of the amplitude balance. Suppose once if I switch off 1 and connect to 5, the amplitude difference will be there. So that is the reason this particular fellows will do. So this is the type of work which is done. Similar one, why can't we have for millimeter wave? When people say that 800 meters, 900 meters are in the, looking at the, what is it called, cellular, this thing, we have got 3 in the towers, you see, what a number of antennas we use to have a sector antennas. The same principle we can have it here. Instead of sector antennas, we can have much more flexible switching type of antennas here, right? This type of work. Now we'll get into the electronic steering. One is that time delay steering. I already mentioned, where the true time delay. In the time delay steering, what will happen is requires a switched lines, right? Switched lines, and it is relatively lossy method, and it is very high cost. See, if you see, when input is here, of course, in the receiving part, same case we can also take the transmit part. If once a signal when fed here, it will go here, and any signal going through here, it gets delayed. Time shift is there because of this time delay, right? So in this one, what will happen is, so this particular one, because of the time shift, time delay steering, this is very bulky, right? And phased array radars, this is time, you see, if you want to have 8 to 18 gigahertz, this is okay. 26 to 40 gigahertz, 18 to 40 gigahertz, this is okay. But, hello? Radars do not need such things. They will have phase shifters are good enough for us. Here, for the phase shifter, it is 2 pi d by lambda, means 1 to other progressive phase shift. Just in the beginning itself, I introduced this phase shift concept, right? So, means electronic beam steering can be done using the phase shifters and the time delay elements, right? While doing this, we can have 2 things here. One is that radiating elements, dipoles, right? 1 second, please. Sorry. See, all these things are good at microwaves, but when we look for the millimeter waves, we need to have either radiating slots and patches and notch type of radiators. These are the things which we look at it. Mostly, most of the things people use the either slots or patches like this, right? Okay, since this is very important one, I have just included the patch radiation is due to the it is it is inhomogeneous. We normally take for this, we have already discussed, right, with Professor Anjaneyulu has discussed, but almost everybody knows about this formula, right? We have 2 methods of feeding a microstrip antenna. One is that coaxial probe, and another is that a groove inset feed, right? Here whether this or that depends upon the choice of requirement. I will explain this while when we go for the array formation, either tile formation or slat formation. These are the required, right? Now, what in the beginning itself, we have mentioned that we have discussed that antenna has got minimum 2 parts. One is the radiator part and another is the feed part. So we have got number of types of feeds: constraint feed, space feed, and subarrays, right? In the constraint feed, what we will have is, see, it is something like corporate feed type of thing. This is that corporate feed type of thing. Here, each one will have splitter here. Suppose if I want split, if I want to 4 elements, if I want to excite, I need 3 power dividers, or we can also have 1:4 power divider also. But as it is, this is called these are the constraint feeds. These corporate feed as far as the series feed. Now the cascade of this corporate feed is nothing but is a cascade of power splitters, so that you can have each phase shifter can be independently controlled, right? 5, 2, 5, 3, 5, 4, 5. Whereas in the case of a series feed, the phase shifts are the same in one line. This is normally meant for the frequency scanning applications, right? So the means feeding part is one of the important requirement. A separate control is required here because one is here, so you have to see control here, 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 here. 4 phase shifters are there. We need to have 4 controls. Whereas in the case of series feed, we have single control enough, right? Now, instead of showing a picture, instead of showing a type of whatever the block diagram, this thing is there, it is always better to show some practical materials. Sorry. So this is corporate feed, linear array corporate feed, right? The single element. This is 2 by 2 array. This is linear array. This is 8 by 8 corporate feed array, right? This is 4 by 8 corporate feed or series feed array. Now, when this gets into slowly, we are getting converged to the requirement of millimeter wave arrays, where the number of, suppose if I have to connect this in a different way and using any other elements, we may not get where the space may not be enough, other constraints may come, right? Now, the element pattern in a phased array is very important. In the beginning, what we told is radiation pattern of an array is equal to array factor multiplied by the element factor, right? So when this particular will become very, very prominent when we are scanning the radiation pattern. Sorry, suppose if we take number of elements, 4 element array, let us take it, right? In the 4 element array, the one which is shown here is the total pattern, means array factor multiplied by the element pattern. This is the pattern of a 4 element array. Suppose if I scan it to 30 degrees, let me say that scan it 30 degrees, this directly will not scan up to 30 degrees. You see, the gain will fall, right? Hope you are able to appreciate it. That means gain of the phased array follows the gain of the element pattern, right? So element pattern design is very, very important here, right? Here, suppose if I take, so that is the reason. Suppose if I take the more broader element pattern, yesterday I think we have shown here one of that, automotive pattern up to 100 degrees beam width. So that type of patterns are required here, right? One of the broadband microstrip antennas is a radiating patch, right? A slot in the ground plane is a feed line. This is also one aperture coupled antenna, aperture coupled broadband microstrip antenna. Now we will get into, now for a phased array what we need? We need radiating elements and we need phase shifters, right now. Actually in the modern phased arrays we may not need phase shifters all the time. We may need only certain other things, right? We can implement phase shifters in the digital domain. That is the reason I'm not considering much of the phase shifting properties here, except one, again, when we go to liquid crystals, there the phase shifting comes into picture. Otherwise, what will happen is, suppose this is a, for the digital phase shifter, we'll have some bits, number of bits, right? 2 to the power of n. Suppose if I got 4-bit phase shifter, means 2 to the power of 4, we have got 16 levels of phase shift starting from 0 to 335, something like, right? So here, if you see, let us take each one will be, see, this can produce lambda by 16, lambda by 8, lambda by 4, lambda by 2. Lambda by 2 means 180 degrees. Suppose if I connect straight here, connect without this, only I connect like this will give 180 degrees phase shift, right? In addition to this one, if I also connect this and this, 270 degrees. 270 degrees plus if I connect this also 315 degrees. This also if I connect 315 plus 22.5, 337.5. So the total is equal to 15 by 16 lambda if I put all ones. So the 16 levels means it is a in the quantization level of 22.5 degrees phase shift. This can provide like this. Mostly people use so far 4-bit phase shifters and 6-bit phase shifters up to 6 bits I have seen, right? Another this thing is the ferrite phase shifter, diode phase shifters and ferrite phase shifters. Ferrite phase shifters are more popular, right, at frequencies at S-band and above, right? The advantage is ferrite phase shifters have better power handling capabilities, and Rajendra Radar uses these ferrite phase shifters which are developed by IIT Delhi, right? So these diode phase shifters are very well suited for MICs and MMICs. MIC stands for microwave integrated circuits. MMIC stands for monolithic microwave integrated circuits, right? At higher frequencies, losses will increase, power handling capability will decrease for the diode phase shifters. But okay, this is what they are available, right? Now, we need to look at it that mutual coupling. Suppose why I have taken the bigger things means we can easily, the same thing holds good for the millimeter wave antennas, where suppose if I take 28 gigahertz or 30 gigahertz, it is 0.5, the element size itself is 0.5 lambda. So if I can't show, again I have to, what is that, I have to enlarge it. I assume that this is a typical phased array, ballistic missile early warning system radar, and this is the array phase of it, right? Okay, this has got bigger histories. This is 1970s wala hai, and another this thing is a Cobra Dine radar array. So forget about all these things. Suppose if this element is excited, it will not just to radiate all alone. Its element will be, its radiation will be coupled to the nearby friendly radars, friendly elements. This is where we call the mutual coupling, right? The mutual coupling, when we explain the mutual coupling analysis, while doing the analysis, first of all, we will exclude that there is no mutual coupling, no interaction between radiating elements. Otherwise, we can't proceed further. But afterwards, we have to take. Now, the mutual coupling is the effect of one antenna element on the other. Suppose, let us take one element. If we excite this element radiates and also couples to the nearby. That means, what does it mean? What does the coupling means, right? Sorry. Right. See, what happens when this radiates, the current from one element, current in one element depends on the amplitude and phase of the current in the neighboring element. Suppose this element itself has its own current, let me say the black one I showed. Because when this radiates, the blue one couples here, the blue one current also flows here. The net current is equal to the black as well as the blue. It may, depending upon the phase, it may have what is that called, increasing effect or decreasing effect. But overall, when the antenna is scanned from the broadside, the mutual coupling can cause change in the antenna gain, beam shape, side lobe level, and radiation impedance. This is the very, very big, work itself, but nothing to fear nowadays. All are, our software packages are there. Sometimes the mutual coupling can also cause scan blindness. Means we thought that we are illuminating in a particular direction, but there will be a null because of the interference, right? Okay. Now, phased array characteristics, let us take. Slowly getting into the, so far, without naming what arrays, arrays, phased arrays. What will happen? Why we need the phased array? For agile beam scan, control of the side lobe structure, multiple simultaneous beams, high power capability, conformal arrays. These are all the features for different phased arrays we need, right? If you look at it, if you use faster scan, what is the use of this one? Suppose, why faster scan? If I tell that, let me say that if let me say I have an antenna here, right? If I radiate in one direction, right? If the target is in the other direction, I have to rotate the antenna. For that particular, for surveillance radars, the antenna rotation rate is as much as 6 RPM, 6 revolutions per minute. Means for every 10 seconds only you can see that particular direction. That is huge S-band antennas. And another X-band antenna which I showed earlier yesterday, 40 revolutions per minute, right? Almost in every 1.5 second, you will be able to cover that like that. But in any case, in between that, high-speed targets we will miss, right? The limitations are there for every application. There will be a limitation. For instance, control of side lobes. The whole pattern depends upon the phase distribution, amplitude and phase distribution. Phase distribution depends upon the number of cable lengths and what not. So by cutting the accurate cable lengths, all those things are very challenging problems. So the phase and amplitude control is a bit difficult, right? Okay. So that requires phase control and amplitude control, right? And another one important factor in our this thing is in the total our education and everywhere is we do not consider the cost, which is the most important one, dictates everything, right? Suppose if I want to buy a smartphone, okay, iPhone, oh my God, it is about some 45,000 rupees. Why, when I am getting with 10,000 rupees, why can't I use that? But it has got its own. Means every performance is associated with a cost. That is the way as technically we should look at it, right? These are all some of the X-band up to X-band arrays which are in principle. So for the tactical applications, I will not be dealing with this. This only for information I am telling, because the topic is we have to discuss more on the millimeter wave arrays. So But if you look at it, here itself the array elements or 10,000 elements are there, maximum number of elements here, the where we are seeing here X band, X band, X band. When X band can take 10,000 elements, X band, let me say to 10 gigahertz, if I go to 30 gigahertz, can I not have definitely 30,000 elements or 40,000 elements, or will it be difficult for me? The idea of showing these things is when we can have such a big ones in so thousands of elements, can we not have the higher frequency? As the frequency is increased, the antenna size is decreasing, right? Now, let us get into technology part of it. So, with 1960s and 70s, these are called passive array technology, right? Now, between 80s and 90s, 2000 active array technology. From 2010 onwards, we have got digital array technology. Now, though we have, I am showing it here with the digital array technology here, some of the passive technologies are being used for a millimeter waves, even in 2010s, now also, certain applications. Everything is not digital here. What will happen here is, after doing this, the phased array technology developed in the early 1960s and 70s for use in the large missile warning and space surveillance radars, right? Okay. Now, if you see this, modern phased array technology, this includes everything. This is a multidisciplinary area, this technology. Here where RF, microwave engineering, please do not get into this. There is no millimeter wave engineering. I said there is nothing like that. Microwave engineering will take care of millimeter wave engineering as well. Digital mixed analog and digital VLSI fabrication, millimeter wave circuits testing, direct current to MM wave circuits. This also includes microwave and millimeter wave engineering, semiconductor device physics and materials, power distribution, computer science, thermal management, and several more disciplines are required. Earlier, the antenna engineering is one mechanical engineer, one antenna electromagnetics engineer, that would have been fine. But the things have changed. We need many people here, right? Okay. Now, coming into the this thing is there, passive phased array technology. In the passive phased array technology, this was the earliest technology where we take one transmitter, high power transmitter, and we use a duplexer, means this isolates the transmitter from receiver. Let us talk in terms of a radar. While transmission, power is coupled to the array, right? Here, let us take it as a, this itself is, suppose we are showing for a large arrays, we cannot have directly from here to single individual elements, we will have some subarrays. Subarray to the element in between phase shifters are coming, right? That means whatever the power we generate here, there will be some loss in the duplexer. Suppose if I have 100 kilowatts power transmitter, my duplexer will also should withstand this particular high power. Got it? Then suppose from 100 kilowatts, if duplexer has got 3 dB loss, 3 dB means half loss, output of this power will be how much? This will be half of this one. Suppose 100 kilowatts will become is only 50 kilowatts. 50 kilowatts, again, it has to be routed through the transmission lines, maybe comes it for 40 kilowatts. And this here also this is a distribution. Then phase shifter will have our 1-2 dB. So ultimately the power reaching here will be very, very, very small. That means a lot of loss will take place. But in the 1960s, in the beginning, this was the only technology we have. After going forward, what we say is, we have a good motorbike now and we compare with the old one. Definitely for the upgraded ones. Here, what will happen is, in the passive phased array, looking at the modern block diagrams, this is the conventional block diagram. Still, we have a TR type of module or whatever you guess. In the transmit side, it will come coupled to the transmitter. Through the circulator, it will connect to the beamformer, analog beamformer, right? So while in the reception, it will come and digital receiver exciter. Exciter is responsible for transmission, receiver is responsible for reception, right? Following is the digital signal processor, right? This is one of the huge array, right? SPY, this is now SPY-6 is the latest one, but this is not. Patriot missile defense radar is very interesting radar. This has got couple of millimeter wave modules also here, this and this, right? This has got, this is for the linear array for identification friend or foe. This is about some 4,000 or 5,000 elements are there. This is meant for tracking and guidance. This is the fire control radar. Based on this requirement, a missile can be released with this one, right? These Patriot missile defense radars are used in Saudi Arabia during the Gulf War conflict, right? Our Rajendra radar, developed by LRD, DRDO, is equivalent to this radar. Even in some ways, it is, our radar is much flexible and better than this particular radar, right? This is meant for air defense applications. This was fielded, why I am showing this here, this was fielded in 1976. Can you guess? Still it is operational. Operational in the sense, it is not without touching knife. Every time it is getting upgraded, except the frequency. When the microwave things are getting upgraded, this is also getting upgraded now. Okay, good. We have seen this, passive phased arrays. Now, what is that wrong with passive phased arrays? We are telling today. I already explained to you that because of the centralized power, if this power fails, the entire array is blank, right? Entire array is blank. This is one part of it. That means reliability point of it. But I'm telling it like this, but at the same time, I'm also telling that the one which is, commissioned in 1976 is still working, right? Looking at the modern ones, we have to tell modern technology. It is happening here. That means that the downtime is heavy. Sometimes it is, but when the transmitter fails, this does not work. Then immediately you have to attend to this one, right? So such things, out of experience from these things, we are, this thing. And low loss beamformer networks are large, heavy, and difficult. Suppose I can have a cable which is somewhat like bulky, circular type of, waveguide. 0.5 dB loss means the diameter will be very high and heavy. It will be heavy. Hello? The RF losses, just now I told that RF losses from the generation point to the antenna input is a huge loss will be there, right? Then what to do? In such a scenario, there are requirements that there is a defense projects, Advanced Research Projects Agency, DARPA in United States. They have initiated certain projects and invested some money, right? In these things, there itself, they have included millimeter wave programs, right? Defense Advanced Research Projects Agency has initiated 3 programs. One is 1988, 93, and 95. The first program was initiated in 1988 was microwave and millimeter wave monolithic integrated circuits, MIMICs, right? Around the same time, our IIT Delhi has worked. Yesterday, I showed you a couple of books also from Professor Bharati Bhatt and Shiban Kaur. It is not that we are totally away from that, but we have been closely monitoring because of our budgets are small and our country policy is like that. We do not have so much of things here. Another this thing is high density microwave packaging program, right? Yesterday also AIP I mentioned, that is out of this only, antenna in package. And another this thing is microwave and analog front-end technology, MAFET. These are the three programs which led to the active phased arrays, right? In the active phased arrays, what will happen is simply the transmitter which was here was, right, shifted straight to this place, to the near to the element. You can see transmitter which was here, right, is shifted straight to the near to this one. That means this duplexer and all these things are not, I mean, that loss we are avoiding. Generate and why to avoid here, why to make the problem here is now, see, and each element is provided one TR module, trans receiver module. Instead of giving a central transmitter, each element is having a transceiver module. Like this, suppose if you say, what will happen? Where is the challenge here? Here the challenge is we have to transmit amplifier we have designed, and we have to design a LNA, low noise amplifier, and with green one is the limiter, right? Sometimes it is the protecting one, right? Now again the phase shifter is still there. Whatever the things here, right? Phase shifter is there. This phase shifter plus added some more circuitry, circulator and these things, all together we are making this as a TR module. These TR modules is this is the heart of the active phased array, whether it is for millimeter wave or microwave. This is the one which is very important one. Now this has got the lower RF losses between the transmit amplifiers and free space, right? Earlier transmit amplifier was here, free space was here. Now transmit amplifier is here, free space is here. That means we are covering a lot. This also, since transmit amplifier, it is a active one, active component. Once active component is there, low noise, noise figure will be heavy. When this is shifted here, there is an advantage in the reduction of the noise figure by a factor of minimum 2, right? And suppose if the transmitter fails, everything would have been blind. Here, if there are 1 or 2 elements fails, no problem. Up to 5 to 10%. Suppose 1000 element array, even if we 10% out of 1000 is 100 elements also, if they go bad, still there will be at least some acceptable minimum performance, array performance, right? Now, as I mentioned, that common leg amplifier is produced by MMIC area here, common leg amplifier. This is the TR module. This TR module, the technology developed in the 3 DARPA projects, MIMIC, microwave and millimeter wave integrated circuits, high density microwave packaging, and MAFET program, microwave and front-end technologies. These programs produced this particular type of, this is one, there are many other things are there. Here, the advantage here is, because this have to go through the, MMIC areas, MMIC requirement, foundry requirements are there. That is the reason there is a common leg amplifier. Common leg amplifier means during the transmit, suppose this is the transmit chain, right? Driver amplifier, transmit amplifier. During the transmit, what will happen is common leg amplifier will be connecting here, 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 like this it will go. In the receiving, limiter, filter, LNA, and comes here, phase shifter comes here, like this. So whether during the transmit as well as receive, we definitely need a phase shifter, Phase shifter has to be there. Phase shifter has to be there, whether it is a transmit or receiver. The same thing is implemented here. In addition to the phase shifter, we have some amplifier, small common leg amplifier, right? So with these things, the antennas which have gone to, even the latest one is F35 is utilizing these antennas. Most of these are used for the X-band purposes, right? This is for active electronically scanned radar array. This has got 120 degrees field of view, right? and it operates at, it range is 200 kilometers to 240 kilometers, right? Well, this has got 1956 TR modules, right? TR modules. And the other one, this is shown in a very, very recent, this is F-35 strike aircraft. It is yet to be, inducted into the services. Japan has already ordered 108 such flights. For this, the phased array, active electronically phased array is improved over this one. Here, if you see this one, a range of 400 kilometers can be done with gallium arsenide modules. This does not have gallium arsenide modules, whereas this has got gallium arsenide modules. Then coming into this thing, the defense requirements and these requirements or military requirements generally are very expensive due to the procedures and the facilities, other things, materials, whatever you call. Now there is a requirement further. How to do it? 2000 and beyond that. How long this, multi-crores or crores of dollars, we can't spend it. So DARPA has initiated again some more programs. There, gallium nitride on silicon carbide. There is a program called Wide Band Gap Semiconductor RF applications, right? For advancing the gallium nitride on silicon carbide. Gallium nitride is required for high power applications. Another this thing is, we need to extend high power to the higher frequencies. Frequency as much as 500 gigahertz, right? DARPA's nitride electronic next generation technology, this is extending up to 500 gigahertz with operation of gallium nitride with high yield, uniformity and reliability. These two programs were aimed to develop the compound semiconductor technology for high powers, high output powers, higher efficiency. High compound semiconductor technology, not for digital alone. This is for RF technology, semiconductors for RF technology. Once this thing goes on, there will be a problem with the, thermal issues will be there. You must have seen, suppose, Pentium processor has got some fan on that one. If you open the motherboard, that means once the chip is, very, very high density packaging is there, that the heat thermal requirements will be there. So developing that embedded cooling for thermal management is also has become important. Now, this is 2000 beyond only. Most of the millimeter wave developments are very, very recent. Though it is there right from 1870, but usage is 0.001% type like that, right? As the phased arrays incorporate higher power levels digitization, the requirement is mixed signal technology, mixed signal integrated circuits, integrated mixed signal circuits, both analog as well as, means on the same board, we need to have analog functionality as well as the digital functionality, right? That means what? We need to have multi-chip module technology, right? This technology is used commonly for microwave as well as millimeter wave RF systems, where we have more than 1 MMIC has to be mounted on a dielectric substrate connected by wire bonds, right? The mixed signal multi-chip modules consist of both analog as well as digital IC chips on the same, but the performance for high speed and wide bandwidth. Suppose, for instance, this type of, this is extending to RF SoCs, system on a chip, like analog devices has come 7361, something like that. But that is of course not millimeter wave, that is microwave. The latest program is DARPA's efficient mixed signal microsystems is a scalable millimeter wave architectures. This is what I'm going to tell now. First, to get into scalable millimeter wave architectures, we have to study the very large background why we need this. right? Reconfigurable transceivers. So these particular things are very much useful for the things. Now, another is compound semiconductor material on silicon, right? So the transistor scale heterogeneous integration processes to combine high power CS compound semiconductor devices and high density silicon CMOS circuits. Again, silicon is back. See, in between silicon was ignored. Oh, every time, okay, gallium arsenide, gallium nitride, gallium indium phosphide, something. So many things were 3-5 components, all those things were discussed. But the devil is back, right? The silicon is back. So here, what is that commercial time scales means phased array should not be limited to only to the defense requirements. We need to develop these things to the amenable, affordable to the commercial requirements, particularly looking into the 5G technologies. Of course, in 2000 itself, ITU guessed that it is going to be improved, right? May not be 5G that time, but still their vision is very, very broad and long, right? So the requirement is to build a block composed of common modules and reconfigurable interfaces, scalable and customizable. What do you mean by scalable? Suppose if I want to produce 1024 element array, right? So if I want to 1024 element array, 512 elements array, shall I design independently? 512, 256, 64, shall I design? No, I want to do only 64 element array 8 by 8. When if I with the same design, I will populate for 256, 1024, something like that. That is called scalable, which we will be discussing like this, right? Then in this, since with these all programs, the thing has totally changed. Active array, digital subarray, and digital array. Earlier, before active array, it was the passive array. The active array itself has gone to so many changes now. Digital subarray as well as the digital array. Now, a beam can be produced. Now, see summation of, suppose in the receive way. Suppose when it receives, it produces a beam. When it transmits, there will be an exciter here, waveform generator. It is for transmission. So a beam is produced upon signal summation upon reception, through radiation upon transmit. Both ways. This is where whether it is active or subarray or digital array, right? Now, the digitization of the multiple subarray channels enables that what is adaptive beamforming that we have been mentioning from the day for yesterday onwards, space-time adaptive processing, multiple concurrent functions. This multiple concurrent functions is the basis for the multifunction phased array radar, right? Now, the digital arrays talked about a lot for CFAR from Australia, MF-STAR from Israel, and Office of Naval Research from FlexDAR, USA. These big arrays, high budget arrays, were only discussed but never published properly. This is only from the news release. But millimeter wave large arrays are appearing in literature, but they are yet to be adopted for applications. The moment anything ready for field deployment, military things they are not revealing, but this is a commercial requirement, so they are coming up very open. Even before deployment, before realization itself, they are announcing, so that they need the market. As I told yesterday, that about billions of dollars of market is there. 26.4 or 26.5 CAGR is going to be there for antennas, right? So let us discuss a little bit about Army Digital Radar. Army Digital Radar consists of control. This is a Spartan FPGAs. Quadrant. This has got 4 quadrants, transceivers, and RF. So this is only to show that technology how it is going, right? Now subarrays, what will we do is subarrays we generate instead of whenever, suppose where the multiple simultaneous beams over a limited sector are required. We don't have to spend such a huge one for the digital phased array. When suppose I need only little bit, only in this area I need the multiple beams, then I use a subarray, right? In the subarray, what will happen is, digital subarray architecture, the combination of analog as well as the digital beamformer, right? So here it will have both receiver as well as exciter. Exciter is responsible for the transmission, receiver is for the reception, right? Here what happens, the advantage here is, even if the grating lobes appear, the subarray will delete them, it will not allow them. So this is the when the limited volume, limited coverage is required with multiple simultaneous beams. I have 1, 2, 3, 4, 5 beams in a one subarray. Like this approach, this is very cost effective. Then another this thing is that element level digital phased arrays. Element level arrays are, see what happens, I receive the power here or receive the signal here, right? When receive the signal here, I am just giving in the earlier one, it is going to the power divider and all elements together is coming to the one. Here what will happen here, whatever we receive here through the limiter and LNA, digital receiver, digital beamformer, here itself we are storing that fellow. Here itself, this itself will be, here itself the information will be stored, right? So the digital beamforming array, the received signals are detected and digitized and stored at the element level itself, right? TR module element level itself, we can store them for the special purpose, a digital computer and for the desired beams, right? What are all the key features of the DBF? The total formation information is available at the aperture, it's stored at n element, at individual elements. Each element I have got the data on its own, but when we get in the number of elements, anytime I can mix up and form the number of beams. Whereas in the analog, it is not there. It comes only completed the input at only one. Analog beamformer produces weighted sum of these signals and reduces the signal dimensionality into only one. Yes, right. So here the digital what are the advantages here? Operational advantages: improved beam pattern, multiple simultaneous beams. We don't have to additional hardware like number of hybrids, number of fixed phase shifters, which I was mentioning, that is not required. And ultra low side lobes and element pattern, we can correct it at the digital level, right? Digital domain. So many advantages are here, right? I think these also advantages. I think time is another 15 minutes only, right? I have got another, okay, I'll be able to do it. Now, most of the things are phased array radar costing. In the phased array radar, the 50% of the phased array cost is, 50% of the radar cost is going to the phased array cost itself. Within the 50% of this radar cost distribution, 45% is going to TR modules, another 45% is going to boards and cabling. So how to reduce this cost? This is the major issue. I have also given a reference here, right? The implementation of the phased array requires large number of electronic components, multi-layer RF printed circuit boards, TR modules, and RF boards and cabling, right? We have two main configurations, phased array configurations. One is the slat configuration, second one is the tile configuration. The slat approach has the advantage. Slat is this one. Suppose 864, 8 by 8, this is 8 by 8 array, this is also 8 by 8 array. This 8 by 8 array requires 8 boards to implement. Here, single board is enough. Then why people are using this? Why people have not gone directly to this? There are advantages and disadvantages. Here, the advantage is because of the large surface area is available, thermal problems will not be there. You don't have to worry thermal problems, but cost is very high, right? In the tile approach, everything can go behind this one. Cost is very cheap, but there are thermal problems. We need to address both, right? See, in the tile configuration, how we do it? Single element, linear array, panel, and a number of panels, right? If I have to design this panel, I will not do again one more element design. This is where we do it. So in the design cycle, it goes like this: element, linear array, tile, and the complete antenna, right? Now, the 64 element dual polarized panel developed at MIT Lincoln Laboratory. This is again, this is the aperture PCB antennas, 8 by 8, right? 8 by 8 antennas. And this is a tile. Or for the assembly for TR modules, each element has got its own corresponding modules, right? These two are, there is a metallic spacer because the RF interference will be there, coupling will be there. To avoid isolation between the digital backplanes, digital circuitry to the RF circuitry, there is a spacer, right? Like this. This has been developed and the photograph is shown. This is the proof of concept for the MIT Lincoln Laboratory, right? Now, the moment I say that, at each element there is going to be, each element has got its own, what is it called? Its own front end, digital front end. That means what will happen if I have one digital front end here? I mean, this corresponding to this element, there is a digital front end here. All these, data has to be brought together to form a beam. Now, what is the interconnection of the building blocks for the digital front ends, right? We have got number of things are there: systolic beam forming as well as hierarchical beam forming. A 64 element array with 100 megahertz of sampling bandwidth, right, would have about 10 terabytes of total ADC data to process a few beams, right? The mechanical serviceable because everything cannot be at one place. Each element is having got its own chip. So mechanical and serviceability considerations, right, and lead to the physical segregation of the array into a number of digital front ends, right? These front ends are virtually, so normally hierarchical as well as systolic. This type of thing, we will have it. Means digital front end node, one node directly and intermediate processor, because ultimate processor is here. Suppose if I got 64 elements, if I connect all 64 elements, this may not be able to take. Suppose if I got 1024 elements, all 1024 elements, if I connect to a central processor, very difficult. So what we will do is, in between intermediate processors we will use, ultimately we will process this. So this is another big opportunity for the people working in the digital domain, right? Okay. Now, looking at that, fruits of the technology, what will happen is, in 2011, whatever costing at 1 is now at 2020, this is costing almost, if you see this is 0.1, 0.05 means at least, nearly more than 50 times, even 0.1 means 10 times to 0.01 means nearly up to more than 50 times we are getting the advantage of the cost, right? Now, this cost again, I just showed to you one tile configuration as a slat configuration. If I take the cost, relative cost or whatever this thing cost it appears, there are two things. Okay, what is there? I can have air cooled. Slat array air cooled to liquid cooled, it is going to be very, very expensive. Whereas tile array is very cheaper, see 0.25%, means at least 4 times or 5 times cheaper than tile array is cheaper than slat array for the same functionality. So while we work on the technologies, it is not that we take a project and do it. We always should be concerned about the cost of what we are implementing. Now, let us get into one specific millimeter wave arrays. This I have just taken from September edition of Microwave Millimeter Wave RF Components Guide ebook, right? September 2020. What it says that, well, we have, the technology has come up to the level of digital domain. Each element data can be stored at element level, and in the digital domain we can do wonders. But that is again limited by frequency. It is becoming again more expensive for millimeter wave phased arrays. Sometimes, depending upon the requirement, suppose if you have, this is 4x4, 16 element array. In this 16 element array, right, the on chip, see, this is just, 4 elements is exploded here. Digital front end, TX RX front end. Okay, forget about horizontal polarization, vertical polarization, just let us take one polarization, right? If we take millimeter wave front end module, this millimeter wave front end module, it has to, its output has to be connected to the, antennas. If you take this as the place here for transmission, when it takes here 1/2, here again, 1/2, 1/2, this is 4 elements are here. With the 2 elements, here it has to be 1:2 power divider. Passive combined distribution purposes. Then here again, 2 elements are here, doing here. But ultimately, you see this phase shifter, amplifier, right? And receive amplifier and analog to digital converter data can be, we can means down convert it and can store the data here itself, right? Here, the challenge here has been that, this particular one shows that 2x2 dual polarized beamforming front end module, right? The on-chip PCB routing losses are very high at millimeter wave. On-chip PCB. I have a chip here, but I have to route to the different antennas. Chip is very small here. 4 elements are, bigger elements are here, right? So these losses we have to reduce, right? Physically, see, as a result, millimeter wave front end components, there is LNA, power amplifier, and switch. This particular one, this thing, right? And this, the total one, this has to be near to the antenna, right? If you see at 28 gigahertz, the half wavelength is 5.4 millimeters, and at 39 gigahertz, 3.9 millimeters. When such a small these things are there, and the lattice spacing constraints need to the, see, integrated circuit and antenna element co-location creates a thermal challenge. These are the issues. See, we need to have thermal sensor here, right? All these things are required. Now, 64 4x6 LTTC based phased array antenna. I explained this in the context of yesterday's one process, antenna in package, right? Side view, this antenna in package, this thing here, this particular one consists of about 10 layers. First 3 layers of the antenna we are designing, right? Implementing. Other 6 layers or 7 layers are for the other functionalities like ground vias and feed lines and other things, right? Power is also required, right? RFIC chip is attached to LTTC substrate, and this we can have this flip chip technology to feed the antenna array, and beam steering also up to 45 degrees we can steer the beam, right? So this particular antenna has got 14.5 dBi gain, right? We can steer up to 45 degrees. This is one of the phased array application for antenna in package application. Now the requirement is a large arrays, right? Large n arrays means if n square improvement of the effective isotropic radiated power in n element phased array. What will happen is, suppose I have got a 64 element 94 gigahertz silicon phased array. This is now I am discussing about the silicon based phased array technology, right? This can cover 10 meters or tens of meters only, 94 gigahertz 64 element array. But if I implement 64 element to 1024 elements, this can cover even up to 10 kilometers for me. Here, what you have to need to see is gain is equal to as we are increasing the number of elements, n times the gain is increasing. N times the gain increasing is, n square overall improvement will isotropic EIRP is increasing by n square, right? So this is that in the receive mode also signal to noise ratio will be improved. Now, this is very interesting thing. You can see that. We always say that let us take that fixed distance of some 4 meters is taken, right? Let us say Friis transmission formula, there is nothing, everything is in the inside anechoic chamber. I have got an aperture of only 60 mm. At 3 gigahertz, it is only one microstrip antenna. In the same area, I can have 64 element array at 30 gigahertz. See, you can see that. I don't know whether you are able to see if you are in the what is it called, mobiles, right? 1 second, right? Suppose this is the propagation loss. The thick one is due to whether it is TX and RX at 30 gigahertz. This is the theory with this particular formula. If you take, right, means with 4 meters, this much is the loss, right? Between 1 meters, 2 meters, 3 meters, 4 meters, right? Now in this loss, isotropic TX and RX at 3 gigahertz, this much only. If I increase to 30 gigahertz also, this is the only loss at 3 gigahertz as well as at 30 gigahertz, right? Isotropic and transmit and array antenna at 30 gigahertz is the square one. Isotropic and this thing at 3 gigahertz is the triangular one, right? Now, what does it mean, right? Now, array antenna with both TX, if I have here and here, if I have both, 30 gigahertz, I have further improvement of the, reduction of the propagation loss. Means propagation loss will be there, means EIRP, I'm increasing, right? Now, another this thing is when we, Dr. Ramakrishna, can I take another 5 minutes? Hello?
Yes, sir. Yes, sir. Yes, sir. Please.
Now, for the large phased arrays, I told you just now, 64 element and 1024 elements means 8 millimeter wave antennas. We need to have larger arrays. For larger arrays, silicon-based larger arrays, the integrated circuit chip design, there is a limitation on the signal chains. We cannot have signal chains more than, see, if you see January 2004 to June 2020. This is the latest article which I have already given the reference. I think, did I give the reference here? This is the reference here. Right? Expected this up to, of course, they, most of the time, the number of signal chains never exceeded 20-30 most of the time, but the highest one or 64 is the maximum so far. Intel and University of California at San Diego and IBM, these people have got it. The maximum number of integrated phase array signal chains per integrated circuit was the limitation for long range communication. Whatever we are talking about, oh no, millimeter waves cannot go only number of meters. No, we need still kilometers at least where the line of sight exists, right? The packaging containing 64 elements at 94 gigahertz, no, that is the issue now. Now let us get into the concept of the array scaling. The general strategy for creating the large phased arrays by combining the repeatable circuit, that's what I was telling, array scaling. Suppose I have here one array, one phased array antenna tile here. This is, let me say, 4 by 4, means this is 16 by 16, 8 by 8, 64 element array. This 64 element array, I can have, this is actually 6.6 mm. Such things I can have 4 phased array ICs, right? This 4 phased array ICs, this is going to be like a, see, almost slightly bigger than 1 cent of American cent, right? See here, I have shown it here. A 64 element means this is a 64 element array. The same thing here is shown here. that incorporated 4 identical silicon-based phased array ICs, 1, 2, 3, 4 ICs, to create phased array containing 4 times more elements than it could fit in a single IC. Right? This could be tiled with others to contain the large phased array. Means suppose the moment we have here is the interconnection between these two things, that is the signal change, that is what we are talking about. Right? Now, after talking so much, again the beamforming issue. If I have to see, this is the we have discussed about this, high power signal generators, mixed signal, compound semiconductors, right? While doing these things, still we can connect it here, RF beamforming IC to this one, but requirement is here the signal path is very difficult to connect here because of here this is at IF level, this is at RF level, right? What here the requirement here is that RF beamforming frequency conversion, if this can be solved by putting here, a down converting it here. When we down convert it to IF, we can say IF and RF beamforming is much more easier, comfortable, right? And here the challenge is here that LO synchronization. Whatever the LO, local oscillator phase, will directly get transferred to the conversion type of thing. So that is the reason what we do is we take lower frequency reference and scale it up with using the phase lock loops, right? This is a millimeter wave prototype phased array here. This has got package with 4 ICs, right? Here this is the photograph of this one, right? Now another problem which comes is here is, suppose if I have an array to 28 or 30 gigahertz, this is the array size, this is the chip size, this whatever that NL chip size for me to connect to this one. Once if this array, if it from 30 gigahertz, if it goes 60 gigahertz or 90 gigahertz or 120 gigahertz, this becomes smaller. Like here, this becomes smaller. When this becomes smaller, this cannot shrink immediately. The antenna package size is reducing as the frequency increases, this particular curve. Now, whereas inductor based design, this is the another chips rarely the size will be more or less constant, doesn't increase. So where is the question? The problem is for larger arrays, see the ICs, the package for n element AIP tile is proportional to the antenna spacing and shrinks with the increasing frequency. That the lower millimeter wave frequencies, the IC is typically much smaller than AIP tile, right? But as the frequency increases, the AIP tile size is reduced compared to the millimeter wave, that chip size. Then what is the area? So consequently, scaling the large arrays becomes a challenging at high millimeter wave frequencies like 220 gigahertz. Then use of dummy elements is the only option, right? We have to use some dummy elements. These, I think, dummy elements part I have not shown here. Yeah, here 36 dummy elements are used here. Actual requirement is only this. This is a 4x4 array, right? These number of elements only to match the silicon germanium integrated circuits at the bottom of this array, right? So that is another requirement here. These are the some of the sample arrays at millimeter wave frequencies. This shows the 94 gigahertz from IBM. This is from 60 gigahertz from University of California, San Diego, 28 gigahertz from IBM, 60 gigahertz from Broadcom, 90 gigahertz from Bell Labs, 28 gigahertz from Qualcomm, 94 gigahertz from IBM again, H is from EFG, okay, H 28 gigahertz from University of California, and Intel 73 gigahertz. This is again unique chip, nobody has gone, this frequency seems to be totally away from others developments, right? Those who are interested can see this. This is available in the IEEE microwave magazine, whatever the given here, the full details are available here. Those who want to go for research in this area, okay, right now it is only theoretical research. It will be more or less where the things are difficult, still the theoretical research will be accepted to some extent. By the time you register today, by the time another 2 to 3 years when you come across, you will be able to do some practical work as well. Now, another this thing is that, shall I go only for that MMIC work type of thing? Is it compulsory for me? Not necessary. There is some more things are coming up. This is liquid crystal solutions right now. Now here the advantage is electronically scanned phased arrays based on silicon beam forming integrated circuits have got certain limitations. It is not that they are not useless, but they are useful at their own cost. Notwithstanding the flexibility of silicon based electronically scanned arrays, there are two potential things: power consumptions and equipment cost. These things can be overcome for liquid crystals using for 5G. This I have taken from Millimeter Wave RF Components Guide ebook, September 2020, right? Here, I'll just briefly tell here, depending here, this is the radiators we have been seeing. The difference is that we are going to have, instead of TR modules, we are having the LC phase shifter stack. This is the difference here, right? This LC phase shifter stack, how does it work? This works from the threshold voltage. When the applied voltage is less than threshold voltage, this is the orientation of the liquid crystals. As you increase a threshold voltage, means they reorient. At a particular stage it is totally, that means by changing the bias voltage, right, greater than or less than or within the limits of the threshold voltage, we can continuously scan. Instead of getting the discrete phase shifter values, we can get a continuous phase shift values, which are very, very important and very useful here, right? This is the very important requirement. Now, this has been already produced, right? Here, the advantage is that the LC technology is passive and biasing and very low power. Just 1 second, I think I am getting a call. Srinivas Raju. లేదు అది నాకు అది నాగేంద్ర చెప్తానని చెప్పాడు, ఒకరినే చేయమని చెప్పాడు అన్నట్టు, ప్రెజెంటేషన్ ఒకరే ఇవ్వమని చెప్పారట. ప్రెజెంటేషన్ ఇప్పుడు ఒకరే ఉండమని చెప్పారట, తర్వాత మనం వి విల్ జాయిన్ ఇన్ ద డిస్కషన్ స్టేజ్లో, రైట్ ఓకే. Sorry. Here the advantage, 1-2 minutes I am going to conclude this. The LC technology is based on passive biasing with very low power, controlling up to 512 radiating elements, consumes less than 0.5 watts. This much of thing is not feasible here in this thing, and the losses are also very less. Here point to point for 5G applications, point to multi-point. Point to point is fully analog architecture. Whatever I have explained there in the beginning, though I have not mentioned whether it is microwave or millimeter wave, the concept is same. Fully analog architecture is suitable for the single beam cases for best cost and simplicity. For point to multi-point, this thing is that for each subarray, the beam flexibility we have got, means each beam for one user. So using LC phase shifter technology, much lower cost, consumes less power compared to MMIC approach. Here the advantage is that this does not require LNA, PA and T/R switch, right? Beam forming architecture does not require this for every element rather than for each subarray. There for every element was having, I have shown here earlier, every element long on. Here every element has got this thing, where that is not required here. One subarray can have one power amplifier, one LNA, one TR switch. Here, another bigger advantage is 8x8 antenna using, commercial silicon-based integrated circuits consumes 20 watts. Same 8x8 array takes only 5.5 watts for LC antenna solution, means liquid crystal solutions. This is one of the comparison. You can go through this. I have given the reference, right? A 16x16 antenna array will take 65 watts for the silicon based one, whereas for the LC based one, it is only 19 watts. For 8x8, this is that Alcon one 8x8 subarray takes 5.5 watts against that Akinova the 20 watts total power consumption. So power consumption is one of the important aspect for the phased arrays, where if you have enough power, there is no problem, go for MMIC. If you have constraints in the power, go for the liquid crystal. Both are having some parallel technologies. So the advantages are the economy of the scale enables Alcon to reduce LC phase shifter cost by 100 times to around $300 per meter square, compared to semiconductor phase shifters, which are estimated to cost around $30,000 per square meter using 30 centimeters dia wafers, right? Here, the power consumption 5 times less power and 10 times lower cost. So these are very important for that, I think. Now I conclude that we have reviewed the antenna fundamentals, discussed the linear and planar array architectures, some technologies developed over the last 5 to 6 decades, passive phased arrays, active electronically phased arrays, digital arrays we have explained, and millimeter wave phased arrays, both MMIC as well as liquid crystal based arrays we have discussed. So with this, thank you very much for your attention, right?
Now the participants are requested to ask if you have any doubts.
Hello?
Hello, participants.
Okay, so one doubt is, what is the software used in phased
Hello?
array concepts for simulation? HFSS, CST, both will work, right?
So there is one more question.
And
sir.
there is one more question in the chat box, sir.
So
It is
what
asked by
might be
P.
the
Surendra
deviation?
Kumar from BAP.
Sorry?
Yes, sir, you can proceed.
Yeah, I am finding one question is, sir, what might be the deviation from simulated to measured results can be accepted according to slide number 1, right?
Yes, sir.
Is this a question or something else?
Yes, sir. The same question I am referring to that.
Okay, see, this question is, there will be, okay, now I have to share and see that 1 or 2
1 or 2 slide.
slide, just. Right. Here, what are you able to see this?
You have to share your screen, sir.
Okay, let me see. Are you able to see now?
Yes, sir. Yes, sir.
Okay. Now here, this is the measured and simulated. Here, if you see, the thick line is simulated here, right? Our requirement is, we have to always see that we normally measure at a larger range than what we require. Normally the operation will be at 60 gigahertz, 35 gigahertz, or 94 gigahertz. This application is for 60 gigahertz array. At the 60 gigahertz array, the simulated results are better than the, measured results are better than the simulated results, you can see here. Up to this you can see. See, the dotted line is right from 55, 57 gigahertz onwards. This is the one. So the question of not acceptability does not arise it here, right? What acceptability is, suppose if 10 dB is return loss, 11 or 12, here you are getting 15 dB. Still it is better than what you are expecting. So the question what I saw is, we can accept it with positive deviations. Negative deviations, we have to redesign it, right? Is it okay? Means if any performance is better than what is better than simulated, means we expect the simulated results are acceptable to us. Better than simulated results are bonus, right? Less than simulated results, we have to go for redesign. There is no question of accepting, not accepting. Okay? Right?
Okay, so there is one more question from
LC versus
Amira
polymer based
Anju.
substrates at millimeter wave technology, right?
Yes, sir.
Oh, well, both are, see, again, whenever we talk about these things, depending upon the application, LC, there is some requirement that switching time is a order of milliseconds, switching time, whatever the LC realization. Polymer may be better compared to, but when we don't need that high speed, why do we get into that one? So LC versus polymer, we have to first we should take one application, then compare that one. This is what my suggestion is, right? Okay, that VIA concept, I will provide you the reference. You see, when we have number of 100 layers or 200 layers, whatever it is there, again, I should connect. I will share the connection here, right? Share it here. I have to show you one more slide here, right? Yesterday I showed you one, right. Here, if you see here, when we have the via holes, we connect to the ground layer, right? When we have that, substrate integrated waveguide development, those holes will be, conductor pens will be only within the requirement here itself, right? So these ground layers will be the overall the ground requirements. This is where we have to see, and ground vias are, you see, this is ground vias here to here, right? In the others, those are the SIW vias are not shown here. For that particular application, if you show the conductor painting, and those will be within those layers only, and that ending layer will be connected to the ground layers. Okay, and I will provide you. I request Dr. Ramakrishna to give the reference. I mean, my mail ID to you. Please write to me. I will give the reference for more details. Right?
Sir, thank you, sir.
Thank you.
Yes, sir, thank you, sir. Thank you, sir. Okay. Sir, one more thing, sir. Beam steering algorithm can we adapt for these Santa systems, sir?
Beam steering algorithms, yes. There are number of beam steering algorithms. That is actually interesting. Beam steering algorithm is the phase array is required for that only.
Oh. No, sir. Actually,
you mean to say that LC type of things? See, wherever the phase shifters are there, wherever the TRs are there, we have to definitely go by that one. Beam steering one algorithm is required. Okay.
Okay, sir. Okay, sir. Thank you, sir.
Participants, if other participants have any doubts, you can raise.
You can also ask me after later also, no issue, because we are available. I would like to promote this antenna activity. This is my passion, right?
Okay, Lakshminarayan Garu, thank you very much, sir. Your experience, your knowledge in this field has really explored many new research areas in the field of millimeter wave technologies. Thank you very much, sir.
Thank you. My suggestion
Your
is
research experience.
Gudlawalleru Engineering College is a very famous college. right?
Thank you, sir.
Make some 1 or 2% activity with this. After this one, please take it up millimeter waves. Any activity on millimeter wave, at least start from 18 gigahertz, 35 gigahertz. I think I find a good antenna book also in your bookshelves, right?
Yes, sir.
I'm able to see, right? We will have
Yes.
a continuous, more interaction.
Thank you very much.
Thank you very much.
Thank you very much. Thank you very much, sir.
I'm disconnecting, right? Right.
Thank you, sir. Participants, we will start the afternoon session with Professor S.B. Gupta from IIT Bombay. We will start at 2 o'clock, and I request you all to join by 1:45 p.m. Thank you all. Rashik sir, you can stop recording. Thank you, sir. You can close the session.